Today I'm going to talk about interference of light. You see, it's a big concept of light, and there's a lot of importance of this concept in physics. Without knowing this concept, we would not have discovered the gravitational wave, which we just now discovered. There we use a concept called interference of light. With the help of interference of light, we got to know that the gravitational waves do exist. And similarly, there's one more of the most important concept that is related to the interference of light, that is the concept of ether. Actually, we used the beautiful property of light, that is interference, to find out whether the ether is existing or not. And there's one more beautiful application of this phenomena, interference of light, is that have you ever thought, how do we know that what kind of elements and what kind of so whatever the planet, whatever the star is having, our star sun is having hydrogen, helium, we say all these things. But did you ever got a doubt like how we got to know all about this thing, or whether we went there and have collected some samples of hydrogen or oxygen or carbon, these kind of thing? Or so instead of that, what we do is we collect light from the star and we try to study the light. And after studying the light, we'll get to know what kind of elements are there in that star. So to understand, see, there is only one thing that is coming from the our sun or any other star from any other galaxy. If you want to know about that galaxy, and if you want to know that whether that planet is habitable or not, there is only one source that is coming from that star to us, that is light. If you somehow can unlock all the mysteries of light, it means that you can find out what's going on in that galaxy. So that's our idea, okay, of understanding light. So the most important concept in that is the interference of light, okay. So the technique by which we got to know the elements of that star is called the interferometer, okay. And there's one more application, there's a lot of applications of the phenomenon of interference of light, okay. Likewise, slowly we'll jump into the phenomenon of diffraction, and I'll tell you how much important it is to understand physics, and there are polarization and all those things. We'll come to them slowly one by one. So for now, we are trying to understand the interference of light. You see, in the early days of physics, there was a big contradiction was going on between the scientists. There's a theory called Newton's corpuscular theory, which is suggesting that light behaves as particle, and we believed on that theory in those days, and like we still believe in that theory as a different thing. You'll get to know all about the particle and wave duality of light. It's beautifully merged in quantum mechanics. When you deal with the quantum mechanics, you'll get to know beautifully what it is all about. But for understanding this light, so there was a theory called Newton's corpuscular theory. Actually, Newton proposed it, and according to this theory, Newton was saying that the light behaves as particle and it is made up of small particles, okay. And with the help of that theory, he explained the phenomena of reflection of light and the phenomena of refraction of light completely without any doubts. But with the help of that Newton's corpuscular theory, which demands for light to be particle, we can't explain the phenomena of interference, and we can't explain the phenomena of diffraction, and likewise we can't explain the phenomena of polarization, because there is something missing about the light, and because we missed out something, some property, that's why we are unable to explain the phenomena of interference, diffraction and polarization. So after Newton, there's a scientist called Huygen came into picture with his new theory and completely against the Newton's corpuscular theory. His idea was, Huygen was saying that according to his theory, light behaves as waves. Okay, but Newton is saying that light behaves as particles, so that's why there is a contradiction between them. Okay, so we don't know the answer, like at that particular stage when Huygen gave his theory. At that particular moment of time, we don't know whether to believe on particle nature of light or to believe on the wave nature of light. So we, like in physics, if you are giving some law or rule, it should be applicable everywhere in the universe. If that law or that rule is not completely explaining or satisfying some physical properties which is going on in daily life, it means your theory is failed. So that is what happening with Newton's corpuscular theory. That's why to explain the interference phenomena, we should do some changes in the theory of light. So that's why the Huygens idea, by using the Huygens idea, we we have successfully explained the phenomena of interference of light. So we'll start with the problem and we'll see the solution. Okay, now the thing is, according to Newton's theory, particles and Huygens theory, saying that light is a wave. So the solution came up for this problem, and the person who gave the solution for this problem was Young. Young performed an experiment which we call it as Young's double slit experiment, and with that experiment he actually proved, and that experiment is demanding for the wave nature of light. So I'll tell you how it is. You see, the Young's experimental setup was something like this. Young's took two slits. There's a slit 1 and the slit 2, and there is a light source here. Light is coming in all direction, okay, three-dimensionally, and here's it is having two slits. It means from this particular area light can go, and from this area, from this there's a block in there, from here light can't go, and from here the light can go, and it'll be having a final screen over there. On the final screen, so this was the setup. First we'll see the particle nature. First we'll see the particle nature, and whether this particle nature is completely fitting into the experimental results. We'll try to see, okay, if this particle nature is not experimentally satisfying what we have actually got experimentally in the lab or the final screen, then we have to disagree with this idea. And if the wave nature if the wave theory is completely explaining what is on the final screen, what kind of pattern we are getting, and if with the help of the wave nature that pattern is completely explainable, then we can say that the light is having the wave nature. So that is what they were trying to Young's trying to prove with the help of Huygens idea. Okay, so be with me. So for for the instant, for now, we'll think that light is made up of particle, and that particles I'm replacing it with small bullets. Okay, just for getting the idea. Okay, so suppose I have a source of bullets and completely I'm shooting in all directions. Okay, these small dots are my bullets, and these bullets are coming from the source of light. So so these are the bullets going there, hitting the slits. So we know what our common sense will tell us is that the bullets which are hitting on this particular surface can make it through, and they will end up on the final screen like this, and at this particular position only, exactly opposite to the slit, will be getting all the bullets which got entered from the first slit, and similarly from the second slit will be getting all the bullets here which got passed through the slit too. This is what we should observe experimentally according to the particle nature of light. But this is not what's going on. There's something else. You see, light has a peculiar property. It's not that much easy to understand it, but we'll make it simple. Just kind of muska, you can understand it. You just have to be with me. So instead of getting these at some particular two spots, all the lights here and there, instead of getting this, what we are actually getting on the final screen is a pattern something like this. Suppose this is the center, I'm calling it as O. So this is not what you are actually getting. It means what? The idea that light is a particle is not true, because if we consider the particle nature, we will get just two spots on which the total light is hitting. But that is not what we are getting on the final screen. This is what we are getting in the lab. By observation, we got this figure. These regions are the dark regions where you don't have any light. These are the bright regions where you have light, and they are equally spaced. Equally spaced means if this dark region is having width of for example 1 nanometer, this will also have 1 nanometer, and the bright will also have the 1 nanometer. So these are the dark spots. We call it as fringes, dark and bright fringes. So we are actually getting, this is not correct, the particle nature. So with the help of the wave nature, we'll try to see whether the wave nature can explain the fringe pattern on the final screen. If that wave nature, if we consider the wave nature and we can successfully explain this pattern of light on the final screen, it means we have to go through the wave nature of light, and we have to cancel it out. The Newton's idea, whether we can prove with the help of wave nature, whether we can explain the fringe pattern. So these are the waves, light waves. They are coming and hitting here, and with the help of this wave nature we can explain the interference pattern, and we'll come back to it. With the help of the wave nature of light, we can explain the interference pattern on the final screen. Why we got the dark and bright fringes on the final screen, we can give the answer for that question, which if we consider the wave nature of light. How this idea works actually, to understand the idea with the help of the water waves. So just before jumping into the wave nature of light, we'll see the wave nature of water waves or water, and after getting the idea of the water waves, we'll jump into the light's wave nature, because it will be bit easily digestible for you guys if we jump from wave water waves to the light waves. So we'll do a small experiment. See, why I'm doing this is because I want you to get the feeling for it, not just the bookish definition. If I gave you, if you can write the definitions on the exams and you'll get the marks also, but the thing is you won't get the actual picture, you won't get the concept out of it. So that is what I am going to do here. I want to give you the concept, not just the definition. So that's why be with me, you'll get to know. So before explaining the fringe interference pattern on the final screen, suppose there's a silent water on the tub, and I have there is a wall which is there is a any kind of it's kind of wall which is separating this region with that region. There's a two, and there's a small opening here. Okay, and what I'm doing is I'm producing plane waves, plane water waves from here. So what we have seen in this experiment is that initially, before the slits, we had the plane wavefronts of the water wave in the two-dimensional surface of water, but as they pass through the slit, they will be of circular wavefronts. Circular wavefronts, and the wavelength will be here. This will be lambda, and here this will be lambda. So the velocity of these waves will be exactly same as the velocity of this wave if the wavelength stays the same. Okay. So the you got the idea. Like once the plane waves hit the slit, pass through the slits, in that side of the slit, the waves are no longer plane. The waves become circular, and you see now they are entering into the region where, if you consider the particle nature, you won't get here, you won't get anything in here. But because of the wave nature, the light will be circular after coming out of the slits, so they can go a bit outside, they will fans out after passing through the slits. The waves will fans out. Okay, so now we'll come to the Huygens principle. This is just For light years, this thing is happening in two-dimensional. Okay, the similar thing light will do, but in three-dimensional. So let's come back to the Huygens principle. Actually, it is Huygens Fresnel's principle. According to the Huygens principle, if you have a slit, a single slit, and if you send the plane waves fronts of light waves from in here, plane wave fronts, so he said that according to the principle, each point on the slit will produce a secondary wavelets. Means this point will act like a light source and it will produce light in all direction. Again, these things. So these small dots will act like a light source. Like you have a plane waves coming to the slit. The slit, there's some imaginary. We are just this is not actually happening. This is not possible. Like light emitting light is not possible. Here the light is there, and again that light is emitting light. It is a completely non-digestible concept. But if we assume this particular principle of Huygens, we can explain the we can explain the final screen pattern. So according to this, each point on the slit, these are imaginary points. We can make plenty of them, and these points are acting like a secondary point source of spherical waves. So from here, the spherical waves are coming. Spherical means in three-dimensional. Like water waves are just showing you the circular one, but here you'll be getting waves, circular waves in three-dimensional. Okay, and here this is also so this is called the Huygens principle. Now with the help of the Huygens principle, we can explain the interference pattern on the final screen. So now with the idea of Huygens principle, we are ready to explain the interference pattern on the final screen. Okay, so now we will come to the Young's double slit experiment. Okay, so the Young's double slit experiment was so this is the Young's double slit experiment. We have the two slits, okay, and we are passing a plane wavefronts through the slits. Okay, so as we know that from Huygens principle, each point on the slit will produce the secondary point source of spherical waves. Okay, so that waves, and here's I have the final screen. Okay, let this be the center. I'm calling it as O, and we will consider a point in the first slit and a point in the second slit. I'll call it as A point and this as B. Okay, so there's a light, this point source is producing a light in spherical wavefronts. So from that spherical wavefronts, I'll consider a single light which is hitting a point P on the final screen. Similarly, this point is also spreading out its light in three-dimensional spherical wavefronts, and from those wavefronts, one of the light is getting hit the same point where A did. Okay, so the wave from here, wave from source A and wave from source B. Now we'll get to know the importance of principle of superposition. Young's used the principle of superposition to explain the interference pattern on the final screen. So for that purpose, we have to find out the path. So the path from AP, not AP, you see the path BP minus AP, if this path difference between these two light waves is coming out to be lambda, we will be getting a bright spot there. Bright spot, or we can say the constructive interference will undergo there. Why? On which basis I am stating that? I'll explain you. So this thing in here is the path difference between the wave, this one and this one. This is the path difference. When the path difference between the ray BP and AP is lambda, we are getting constructive interference. So to explain that, we have to use the concept of superposition. Okay, principle of superposition. According to the principle of superposition, if you get top of a wave and the other wave is also having the top, then these two top and top will interfere, will get superimposed, and the resultant is going to be, if this is having amplitude A and this is having amplitude A, but the resultant wave will have the amplitude 2A, because they are trying to go in the same direction. So what I mean by path difference lambda is that if you have, suppose at this particular position, this ray has traveled lambda and this ray has traveled 2 lambda. It means when they reach on the final screen at point P, it has completed its 1 lambda, so it will be at its top, and this one, this ray 2 has completed its 2 lambda, matlab it will also be on its top. So they will both having top and top, so that's why they'll give you a constructive interference. That's why we have studied the constructive superposition to explain the constructive interference. Similarly, suppose if you will get a point on a fine screen where this is 2 lambda and this ray will be 3 lambda. So 2 lambda, 3 lambda, 2 lambda means it will be on its top, 3 lambda means this ray will also be on its top. Again we will be getting constructive. So but before reaching from 2 lambda to 3 lambda, there is some space Okay, there is some space on the final screen where you can't get a round figured value of lambda. You will be getting 0.5 lambda or 1.5 lambda or 2.5 lambdas. At that particular position, you will be seeing destructive interference. To generalize the condition, I'll write here as n lambda. So this is the condition for constructive interference. Whenever there is a path difference between these two rays and that path difference is the integer multiple of lambda, then you can have a constructive interference where n can take values 0, 1, 2, 3 likewise. Where we can have the path difference 0 at the center here. The ray from A will travel some distance and the ray from B will travel some distance. You see the distance traveled by A to reach the point O on the final screen and the distance traveled by the B to reach the point O on the final screen will be exactly same. So it means that at the center of the final screen you are getting a bright fringe, and slowly at the second likewise a bright, then you will be getting a dark. Now we'll see what is the condition like we have expressed mathematically the condition for the constructive interference. Similarly we'll express a condition for destructive interference. So you can guess now. You see B, the path difference BP minus AP should be n minus 1 by 2. This is the condition for destructive interference. So how come you'll see now? You see, similarly, n can take values 0, 1, 2, 3, 4. So if we take n equal to 0, it will be lambda by 2. It can be plus or minus, and this sign doesn't matter. You can have plus or minus anything. Okay, the number. So here we'll be taking plus. So the path difference wherever you are having on the final screen, suppose we'll take a point on this point P, the ray 1 has traveled lambda distance to reach the point P, and the ray 2 has traveled 1.5 lambda to reach the point P. So what kind of physical what kind of shapes, whether the will be getting both as top on the point P or what, we'll see now. Suppose so lambda, it has traveled a lambda distance, matlab the ray is starting from its top, so it will end on its top or at point P, matlab it will be like this at point P. Now the second ray has traveled 1.5 lambda, means its lambda will be at the top, but as its travel 0.5 lambda, its position when it hits the point P, its position will be down. The wave will be moving down, and the wave, this A from the ray which got from A is moving upward, and the ray which is coming from B is downward. Why? Because the lambda because the path difference is 0.5, matlab lambda by 2. So that's why the final will be nil. We know how do you know that the final is going to be nil? Because we have studied in the principle of superposition, destructive superposition will occur. How? This has lambda amplitude A and this is having amplitude minus A. The resultant amplitude or the resultant amplitude is going to be 0. Why? Because A minus A will get cancelled out, that's how. will be getting no amplitude. No amplitude means what? No light. So there will be a dark fringe there. Got it? So this is how Young's explained the interference phenomena by using principle of superposition. If you are using the principle of superposition, that thing on which you are using the principle of superposition, that thing should have the wave nature on it. So that's how we uh, have proved light have the wave nature. So there's a peculiar thing which we can notice in here. There's an interesting fact. Suppose if we consider light as bullet from source A, I'm talking about the destructive condition. One bullet from source A and other bullet from source B is meeting at some point P and giving you no bullet. It means destructive interference. So with the help of the concept, so there's a one bullet plus other bullet and giving you nothing. So that's why we can't explain the interference phenomena by using the particle nature of light. Okay, but if you see, if you take the top of the wave, bottom of the wave, that will give you a zero amplitude. If you take the top of the wave, again top of the wave, it will give you a big top. So that's why we are denying the particle nature of light. Now we'll find out the path difference between these two rays with the help of the geometry of the figure. And with that path difference, we can find out the phase difference, and with the help of the phase difference and the path difference, we can find out so many other things also. That is the beauty. Like slowly once you know a concept, using that thing slowly you can do so many other things also. Okay, so now we will find out the path difference. This is my slit 1 and slit 2. Here's I have the suppose the distance between these two slits is D. The distance between these two slits is D. Just for there's a angle theta it is making, and exactly parallel to this I have another one. This is also making theta, one wave, and the other wave also having theta on this slit, the other slits. So actually you see this ray from slit 1 and this ray from slit 2, they are exactly parallel to each other. So two parallel rays won't meet each other. They will meet but at infinity. Okay, so I want to see the interference pattern with the help of due to these two rays. So what I do is I use some lens in here. This lens will merge these two rays and we can see the interference pattern due to these two rays. Okay, so now we are finding the path difference. So to find out the path difference, the extra distance traveled by the ray 2 is going to be this distance. That is what we have to find out. Okay, using the geometry of the figure. You see, if this is theta, then this can also be theta. How? Because this is 90 and this is also 90, and this is also 90. So 90 and 90, this is theta, that's how this can be theta. Okay, now from this triangle we can write the path difference, this thing, the path difference can be written as d sine theta. Okay, and from this path difference, from this path difference, we know the relation between the phase difference and path difference. The phase difference, denoting it with delta 2 pi lambda into path difference. This is the relation between path difference and a phase difference of a wave. So to get the phase difference of the wave, I'm trying to find out the phase difference between these two light rays. That phase difference is 2 pi by lambda d sine theta. So now I want to find out what should be the phase difference between two rays if I want to have the constructive interference. Should be, so the condition is that constructive interference, the condition is something like this: the path difference should be equal to n lambda. If the path difference is equals to n lambda, then we can have the constructive interference. Now substitute the path difference in there, and that's how we can get to know what should be the phase difference if you want to have the constructive interference, n lambda. So this lambda will get cancelled out. The phase difference should be phase difference should be 2 n2 pi. Okay, if the phase difference between any two rays is this n2 pi, then it is sure that you are going to get a bright spot or constructive interference there. Similarly, we can find out what should be the phase difference to have a destructive interference. Okay, you see now the condition for destructive interference is that the path difference, which is d sine theta, should be equal to n plus half into lambda. Now substitute this path difference in this equation. The phase difference for the destructive interference will be 2 pi by lambda into n plus half lambda. This lambda will get cancelled out. So this is the condition for phase difference to have a destructive interference. Okay, this is for constructive and this is for destructive. We have seen what should be the path difference to have a constructive and destructive interference, We have also seen what should be the phase difference to have a constructive and destructive superposition interference. Now, now we will find out at what particular position on the final screen from the origin, right? So this was the setup. Here I have. So on the final screen, let this be O. So this is my theta. Suppose I'm getting the first dark here. Okay. So I want to find out at what angle I can get the first dark. Likewise, I want to find out at what angle I can get the second dark, or I can also find out at what angle I am getting the first bright and the second bright. Likewise, I want to find out the angles. Why we are doing that? If we can find out the angles and the path difference, that equation will help us to find out the wavelength, and so many other applications are there. Okay, so now we are finding the angular positions of dark and bright fringes. We can call them as dark and bright, or constructive or destructive, likewise. Okay, we want to know the position, the angular position of the first bright fringe. Okay, so the first bright will have some path difference. To have the first bright, what should be the path difference? D sine theta is equals to lambda. Okay, at this particular path difference, we can have the first bright fringe. Okay, so if I send this D to that side, it will go downstairs, and I'll be remaining with sine theta is equals to n lambda. When we do this experiment, we put the final screen so far away from the slit. If the slit and the screen is having a large distance between them, then the angle which this ray is making, the first bright is making, will be so much smaller. So when the angle is smaller, you see, and this is the final screen, and if I have to look at the first bright, I have to look something like this. This is the position of the first bright. But if I do the same experiment, but if I place the screen away from me, so I don't have to look much up. Okay, but if I put the screen so near to the slit, if I want to see the first bright, I have to look something like this. I have to move upward with greater angle. So that's why here in this experiment, the slit and the screen having bigger distance between them, so that's why the theta is going to be small. And we know that when the theta is small, so the theta can be replaced, sine theta, the sine theta can be approximate to theta. So theta is equals to lambda by d. So this is the angular position for the first bright fringe. So because it is for the first, I'll write it as theta 1. Similarly, if you want to do for the second bright, what is the path difference? For the second bright fringe, it will be d sine theta d equal to 2 lambda. Okay, because it's 2 lambda now, the theta 2 can be written as 2 lambda by d. This is the angular position of the second bright. So similarly, if I generalize it, theta n lambda by d. With the help of this equation, you can find out the angular position of any fringe you want. You just give the number. If you want to find out the angular position of the first, give give n equal to 1. If you want to find out the angular separation for the fifth fringe, give n equal to 5. You'll get the angular separation, this angle for the fifth fringe. So similarly, we can do for the we can do for the dark fringes also. If you want to get the angular position for the dark fringes, what you have to do, instead of taking lambda, we have to take lambda by 2. Now we are finding the angular position of dark fringes. So the path difference for the dark fringe is equal to, if you want to find out the first dark fringe angular position, it is lambda by 2. Okay, it is the first dark fringe. Okay, so similarly, theta can be sine theta can be replaced with theta. That's how we can get the first dark, the angular position of the first dark will be like that, and you can find out 3 by 2 t. This is the angular position for the second dark, and if we generalize it to the nth dark fringe angular position, it can be written as n plus half lambda by d. So with the help of this equation, you can find out the angular position of any dark fringe you want. So now I want to find out the linear distance. You see, what I mean by that is, so now I will find out at what particular distance I can have the first bright or the second bright or third bright from point O. So these are my slits. Okay, and this is the final screen. The distance between slit and the final screen, I'm calling it as L. Okay, so this is my point O. Somewhere, suppose here, I'm getting a dark, first dark at position x1. So the angle will be, suppose the angle is theta. We know the path difference is what? From this figure, we know that tan theta x by L. Okay. Now, suppose this is the position of the first nth bright fringe. So the path difference for the nth bright fringe is n lambda. The sine theta can be written as n lambda by d, and we know that for small angle approximation, the sine theta can be written as tan theta. As I told you earlier, that the angle is very small. That's why I can replace sine theta with tan theta. Okay, so this can be written as tan theta is equals to n lambda by d, and tan theta can be written as x by L is equals to n lambda by d, and that's how this x can be written as n lambda by d into L. So this is the position, the distance of nth bright fringe. If you want to find out the distance of first bright, put n equal to, here this is for the nth bright fringe. If you want to find out the distance for the first bright, put n equal to 1, here it will be lambda L by d. If you want to find out the distance for the second bright, put n equal to 2. Likewise, you can find out. Similarly, this was for the bright, and we can do for dark also. So dark fringe, the path difference will change. Path difference will be d sine theta will be equal to n plus half lambda, and sine theta can be written as n plus half lambda by d, and this can be written as tan theta, and tan theta can be written as x by L n plus half lambda by d, and x sub n can be written as n plus half lambda L by d. So this is the position from point O to get. This is the position from point O. With this we can find out the position of the distance of dark fringes. If you want to get the distance of the second dark, put n equal to 2. Distance of the third dark from O, put n equal to 3. Distance of the fourth dark from O, put n equal to 4. Okay, so that's it for today.